Step outside on a clear night, and the sky can feel almost still. A few stars above you, a dark space between them, a silence so wide that it feels empty. But that emptiness is an illusion. Most of what is out there never reaches the human eye. Some of it is too faint. Some of it is too old. Some of it is hidden behind dust, distance, or the limits of light itself. And some of it may be beyond any signal we can ever receive. The more humanity learns to see, the stranger the darkness becomes. Each telescope, each spacecraft, each faint measurement pushes the circle of knowledge a little farther outward, but the dark does not disappear. It only moves. That is the quiet mystery at the center of this story. The universe may not have an edge like a wall. It may have horizons, boundaries, regions that can be measured, and regions that may remain forever outside our reach. So before we go deeper into the dark, take a moment to like the video on YouTube if you want more calm documentaries like this. And if you listen to The Last Signal as a podcast, follow the channel on Spotify as well, because the farther we look, the clearer one thing becomes. We are not standing at the center of certainty. We are standing beside a small circle of light, and beyond it, the universe continues. From the ground, the night sky can look almost honest. It seems to offer itself plainly, a black expanse scattered with stars, planets, and the pale wash of the Milky Way when the air is clear enough. To the human eye, that view feels complete, because it is the only sky our bodies were built to receive. Yet the first great limit in astronomy is not distance. It is biology. The eye is a remarkable instrument, but it sees only a narrow strip of what light can be. Visible light is just one small band inside a much wider electromagnetic spectrum. Beyond the red end of ordinary vision lies infrared light, where cooler objects and dust-hidden regions begin to reveal themselves. Beyond the violet end lies ultraviolet light, along with other forms of radiation that human sight cannot register at all. Radio waves, X-rays, gamma rays, and infrared signals may cross space for millions or billions of years, but to the unaided eye, they arrive as nothing. A dark patch of sky, then, is not proof of emptiness. It may be full of objects that are too faint, too distant, too cold, or too deeply buried in dust for ordinary vision to notice. The universe is not hiding in a dramatic way. It is simply speaking in forms our senses cannot hear. Even before instruments leave the ground, Earth's atmosphere creates another limit. The air above us is not just empty blue space. It is a protective shield, a moving ocean of gases that keeps life alive while changing the light that reaches us. Starlight bends as it passes through shifting layers of air, so that is why stars twinkle. The twinkle is beautiful, but it is also a kind of distortion. To a telescope trying to measure fine detail, the atmosphere is like looking through a pane of glass that never quite stops trembling. This same atmosphere also blocks parts of the spectrum before they ever reach the surface. For life on Earth, that is a gift. For astronomy, it is a barrier. The very thing that lets us breathe also filters the messages arriving from deep space. Then there is the light we create ourselves. For much of human history, the night sky was a common inheritance. People could step outside and see the Milky Way as a bright river across the dark. In many modern cities, that river has nearly disappeared. Streetlights, buildings, traffic, and illuminated signs push artificial brightness upward until the sky turns gray. The stars do not vanish. The galaxies do not move away. The human view is simply washed out by its own surroundings. A person standing under a city sky may look up and see only a few dozen bright points. Above that same person, Beyond the orange haze, the sky is still crowded with structure. The emptiness is local. The blindness is ours. Now hold one small patch of sky in mind. At first, with only the eye, it may look black. A few stars might appear near its edges, and the rest may seem like an absence. Through a good ground-based telescope, more points begin to emerge. The blackness loosens. What looked smooth becomes grainy, with faint light. Then place an instrument above the atmosphere, away from the moving air and far from much of the glow that weakens the view. The same patch changes again. Objects that were invisible begin to appear in layers. Some are nearby stars. Some are clouds of gas. Some are entire galaxies, so far away that their light has crossed space for longer than human civilization has existed. And if the instrument can see beyond visible light, the transformation becomes stranger still. Dusty regions begin to open. Cooler objects begin to speak. Light that had been stretched beyond the reach of the eye becomes measurable. The sky was never the simple black field it seemed to be. It was a crowded room glimpsed through a keyhole. This is why space telescopes became so important. They are not replacements for human curiosity. They are extensions of it. A telescope above the atmosphere carries the human act of looking into a cleaner, quieter place. It gathers signals that the ground cannot receive as clearly. It measures light that the eye cannot see. It turns absence into information. The result is not that the universe becomes larger when our tools improve. The universe was already there. The stars, galaxies, nebulae, dust clouds, and invisible forms of radiation were already crossing the dark. What changed was the width of the opening through which we looked. Each better instrument moves the boundary of perception a little farther outward. Each new wavelength adds another layer to a sky we thought we understood. And the first lesson is humbling. Before humanity can ask what lies beyond the edge of everything we can see, it has to admit how little seeing ever belonged to the eye alone. Some signals from the universe do not arrive in the form they had when they began. By the time they reach us, they have been stretched, thinned, weakened, and shifted into a different kind of message. The James Webb Space Telescope was built for that problem. It was not designed simply to take prettier pictures of space. It was designed to receive radiation that ordinary vision cannot handle, and that older instruments could not fully reach. The central reason is cosmic expansion. As radiation crosses enormous distances, the space it crosses is not still. It expands while the signal is traveling. That expansion stretches the signal itself, increasing its wavelength until what began as visible radiation can arrive in the infrared. This is redshift. It is not paint fading on an old wall. It is the expansion of the universe written into the arriving signal. A simple comparison is sound. When a note is lowered in pitch, it can still carry the identity of the instrument that made it, but it reaches the listener changed. In a similar way, deep space radiation can still carry information about the galaxy that released it, even after the universe has stretched it into a different register. For the earliest galaxies we can study, this matters completely. A telescope that only works well in visible wavelengths would miss much of what has been pushed beyond that range. An infrared observatory is built to listen where those old signals have ended up. That is why Webb is so different from a normal camera in orbit. It has to be extremely cold. An infrared instrument is trying to detect faint heat-like signatures from distant objects. If the machine itself is warm, its own glow becomes a kind of noise. It would be like trying to hear a whisper while standing beside a running engine. The whisper may still be real, but the instrument would drown it in its own presence. To prevent that, Webb carries a large sun shield. The shield keeps heat and sunlight away from the sensitive instruments. On one side, the sun, Earth, and Moon sit behind a protective layer. On the other side, the observatory faces the dark with instruments cold enough to register extremely weak infrared signals. The mirror serves a different purpose. Its broad, segmented surface gathers what little radiation arrives after crossing deep time. The larger the collecting area, the more of that faint information can be caught. In this sense, the mirror is less like a window and more like a receiver. It does not create the message. It waits for what is already arriving. The Hubble Space Telescope changed astronomy in its own way. Hubble gave humanity some of the clearest visible views ever made of galaxies, nebulae, and deep space. It showed that areas once thought empty could hold thousands of galaxies. It turned the remote universe into something detailed enough for the public to recognize. But Webb was not built as Hubble's replacement in the simple line of progress. It was built as a different kind of tool. Hubble made the visible universe feel closer. Webb was built to measure what visible astronomy could not easily receive. The difference matters because dust also hides much of space. In star-forming regions, thick clouds can block visible wavelengths almost completely. Infrared radiation can pass through some of that dust more easily. That lets the observatory study young stars, hidden structures, and distant galaxies that would otherwise remain buried behind the material around them. So Webb does two things at once. It looks far across distance, and it looks through material that blocks ordinary sight. Both abilities are about the same deeper question. What is present, even when the visible sky refuses to show it? Now slow the scale down to a single signal. It leaves a young galaxy when the universe is still unfamiliar, before the structures around it have settled into the patterns we recognize today. It travels outward through expanding space. It crosses regions where later galaxies form, where stars burn out, and where clusters gather under gravity. Nothing pushes it toward us with intention. It simply follows the geometry available to it. Over vast stretches of time, its wavelength lengthens. What began as one kind of radiation arrives as another. At last, after crossing nearly the whole observable depth available to us, it falls onto a cold mirror far from the ground. There is no sound when it arrives. There is no flash that a human observer would notice. There is only a measurement, fragile and precise, carrying a trace of a galaxy almost lost to distance. That is the power of this observatory. It turns stretched signals into evidence. It lets researchers study places so remote that caution becomes part of the discovery itself. When scientists describe the earliest galaxy candidates, they do not treat every faint object as a final answer. They test the measurements, compare models, and ask whether the signal truly belongs to a very early structure or whether some closer object is pretending to be older through its color and shape. That caution does not weaken the discovery. It makes the discovery useful. Astronomy at this scale is not only about seeing farther. It is about proving that the faint thing being measured is really what it appears to be. Webb's images can look beautiful, but beauty is not their main purpose. Their real purpose is information. The shape of a galaxy, the color of a faint point, the way dust glows, and the spread of radiation across different wavelengths all become clues. The oldest messages arrive changed, and the instrument has to understand the change before it can understand the source. That is why this telescope feels so important. It was built for a universe that does not hand us its past in a simple form. It receives signals that have been stretched almost beyond recognition, then asks what still remains inside them. In some regions of space, creation does not begin in brightness. It begins inside cold clouds where gas and dust gather so thickly that visible light struggles to escape. To an ordinary telescope, these places can look like dark stains against a brighter background. To an infrared instrument, they begin to change. The darkness becomes textured. The hidden interior starts to show structure, and inside that structure, new stars are taking shape. A nebula is not only a beautiful cloud photographed in color. It can be a working environment, full of pressure, gravity, radiation, and motion. Within the densest parts, gravity slowly pulls material inward. The cloud does not collapse all at once. It gathers unevenly, forming knots where more gas draws in still more gas around it. Over time, those knots grow heavier. Pressure builds. Heat rises. A future star begins as a hidden concentration, inside a cloud that still looks quiet from the outside. This is one of the strange contradictions of star formation. The same material that helps build the star also hides it. Dust grains cool the cloud, shield parts of it from harsh radiation, and allow denser regions to survive long enough for gravity to work. Yet that same covering blocks visible light from escaping cleanly. The birthplace protects the object forming inside it. It also conceals the process from anyone looking only with ordinary sight. That is why infrared astronomy matters so much here. Infrared light can move through many dusty regions more easily than visible light. It does not make the cloud transparent in every sense, but it opens passages that were closed before. Young stars that seemed buried can become measurable. Jets, cavities, heated grains, and glowing structures can appear where the visible image showed only a shadow. The result is not just a prettier version of the same picture. It is a different layer of the event. In visible light, a nebula may show its outer walls, bright ridges, and illuminated surfaces. In infrared, the observer can begin to see the crowded activity behind those surfaces. This changes how the region is understood. The cloud is no longer just a shape. It becomes a system. Radiation from newborn stars pushes outward. Stellar winds carve into the surrounding gas. Cold material keeps falling into denser pockets. Older young stars begin clearing space around themselves, while newer ones may still be hidden deeper inside. There is no single moment when a star-forming region simply becomes active. It is active in layers, with some parts already burning, and others still dark enough to keep their secrets. Picture the inside wall of a great nebula, not as a smooth painted surface, but as a ragged cliff of gas and particles. Above it, young stars pour radiation into the cloud. Their light eats into the material that made them, slowly shaping towers, cavities, and torn-looking ridges. Deeper inside, colder pockets remain sheltered from the full force of that radiation. In those sheltered places, matter continues to gather in silence. The cloud is being destroyed and used at the same time. It is a birthplace that begins disappearing the moment its children become strong enough to shine. This is why named regions such as the Carina Nebula and the Tarantula Nebula are more than dramatic images. They are laboratories of scale. They show how star formation happens not as a neat, isolated event, but as a struggle between collapse and disruption. Gravity tries to draw material inward. Radiation pushes material away. Winds scrape and hollow the cloud. Dense pockets resist for a while, then either form stars or are torn apart before they can finish. In a region like this, light is not only something that reveals the structure. Light helps reshape the structure. The youngest massive stars burn with such force that their surroundings cannot remain still. Their presence changes the future of the cloud around them. Some nearby pockets may be compressed, possibly helping new stars begin. Other pockets may be stripped apart before they gather enough material to ignite. The process is creative and destructive at once. That dual nature is easy to miss if a nebula is treated only as a colorful object in the sky. The colors used in telescope images often represent forms of radiation beyond ordinary vision. They help human eyes read what the instrument measured. Behind those colors is a physical contest taking place across spans of gas larger than anything the mind handles naturally. The beautiful image is only the surface translation of heat, pressure, particles, and radiation. Infrared observation gives that translation more depth. It lets researchers separate what is glowing on the outside from what is forming within. It can reveal stars still wrapped in their early material, not yet fully exposed to the open darkness around them. And it reminds us that distance is not the only thing that hides the universe. Sometimes the important barrier is not how far away something is. Sometimes it is what stands between the event and the light we can receive. The birth of a star is not always announced by brilliance. For a long time, it may happen inside a cold, thick cloud that seems almost empty from the outside. The universe builds many of its brightest objects in places that first appeared dark, and some of its most important work takes place inside regions almost made to conceal it. A dying star does not always vanish in a single violent instant. For many stars, the end is slower, stranger, and more delicate. The outer layers loosen. Gas lifts away from the hot central remnant. Dust spreads outward into the surrounding dark. What once seemed like a stable sphere begins to open itself into space. This is where a planetary nebula begins. The name can mislead, because planets are not being formed inside it. A planetary nebula is a shell of material released by a dying star. Through early telescopes, some of these glowing shells looked round and planet-like, and the old name remained. But the object itself is not a planet nursery. It is the exposed aftermath of stellar change. A star that spent much of its life holding itself together eventually reaches a point where that balance can no longer continue in the same way. Its core changes. Its outer layers become unstable. Material that was once locked inside the body is pushed outward into space. The result can look almost peaceful from a distance. A ring, a halo, a faint oval of light, a delicate structure suspended against blackness. Yet inside that appearance is a powerful transformation. The object is losing what it once was and giving the galaxy something it can use again. This is the part that makes stellar death more than an ending. The released gas and dust carry chemical material outward. Elements formed or carried within the old body spread into the surrounding environment. Over time, that material can mix with other clouds, join new regions of gas, and become part of later generations of stars and planets. The calcium in bone, the oxygen in air, the carbon in living tissue, and the metals inside machines all belong to a universe that does not keep matter in one form forever. The galaxy changes because older stars return material to it. Death becomes part of construction, not in a mystical sense, in a physical one. The same atoms that drift away from a fading object may one day become part of a world that has oceans, rock, storms, and chemistry. Infrared and near-infrared observations help reveal this process in ways visible light alone can miss. Dust inside and around the nebula glows at wavelengths beyond ordinary vision. Structures hidden in the shell become easier to study. Researchers can see where material is warmer, where it is clumped, and where the expanding gas has been shaped into patterns that are far from simple. Some planetary nebulae appear almost symmetrical. Others look twisted, uneven, split, or carved into lobes. That complexity often points to more than one force at work. A companion star can change the shape of the released material. If two stars orbit closely enough, gravity can stir the expanding gas instead of letting it drift outward evenly. The result may be rings, arcs, jets, or hourglass-like forms. These shapes are not decorations. They are records of interaction. They show that even at the end, gravity can write structure into matter. Stand for a moment beside one of these glowing shells in imagination. There would be no sound, no wind would brush past, no flame would roar. Only a thin, expanding veil would surround the hot remnant at its center. The shell would keep spreading, becoming wider and thinner with time. Its edges would soften into the dark around it. What once belonged to one object would slowly stop being separate from the space beyond it. That image can feel mournful, but it is not only mournful, it is also a form of release. The old body can no longer hold its outer layers, and the galaxy receives what escapes. Inside that release is a kind of inheritance, not a planned gift, not a message, just matter obeying physics and becoming available again. This is why the life and death of stars cannot be separated cleanly. The cloud that forms a star may contain material from older ones. The star that dies may feed a later cloud. The later cloud may build planets around another young sun. A world that feels solid underfoot can carry the remains of objects that disappeared long before it existed. The cycle is not neat, and it does not happen quickly. It unfolds across spans of time so long that human history is only a flicker inside them. But the pattern is clear enough. The universe does not create everything from untouched material each time. It reuses, it mixes, it breaks apart, and gathers again. A planetary nebula is one visible sign of that larger circulation. It marks the moment when a star's private material becomes part of the public supply of the galaxy. For a while, the shell glows, then it thins. The central remnant fades, the structure becomes harder to see, and the material keeps moving outward, no longer a clear object, but part of the surrounding medium. What looks like an ending is also a transfer. Older stars do not simply disappear into silence. They leave the ingredients from which later worlds may be made. At a certain distance, the universe stops offering stars as separate points. The scale changes. The familiar units disappear. What once seemed like individual lights become something larger, dimmer, and harder to separate. Whole galaxies become the objects. A telescope no longer studies one star inside one neighborhood. It begins to measure entire systems at once, each holding gas, dust, old stellar populations, young regions of formation, and hidden structure bound together by gravity. This change in scale is one of the quiet shocks of deep astronomy. Nearby space can feel almost personal because a single star can be named, measured, and imagined as a sun with its own possible worlds. Farther out, that intimacy fades. The universe begins to appear in collections, disks, swarms, arcs, clusters. Light stops looking like a point and starts behaving like a record of structure. A galaxy is not a fixed decoration in space. It moves, it turns. It responds to gravity from nearby systems. It can be stretched, disturbed, stripped, or pulled into new shapes by another massive neighbor. When two large systems pass close to each other, the stars inside them usually do not collide directly. The distances between stars are too large for that. But gravity still reaches across the gap. It pulls on gas, It bends spiral arms. It draws long streams of material outward. It can compress clouds strongly enough to trigger new waves of star formation. From far away, an interaction may look frozen, like a strange shape caught in a photograph. In reality, it is motion slowed to a scale the human mind cannot naturally follow. What appears still may be a transformation unfolding across millions upon millions of years. The same idea grows even larger in galaxy clusters. A cluster is not just a group of objects sitting near each other by chance. It is a gravitational environment. Hundreds or even thousands of systems can share the same region, moving through a common field of attraction. Between them can lie hot gas, invisible mass, and forces that shape how light travels through the cluster. At this scale, gravity becomes more than the force that holds objects together. It becomes a tool for seeing. This is gravitational lensing. The idea is difficult only because ordinary life gives us no direct experience of it. Mass bends the path of light. A large concentration of mass, such as a galaxy cluster, can sit between Earth and a more distant object. Light from that farther object does not always travel to us along the straight route we would expect. It follows the curved geometry created by the mass in between. The result can be magnification. It can be distortion. It can turn a distant source into a stretched arc, a duplicated image, or a faint curve around the cluster in front of it. The telescope receives the distorted pattern, and researchers work backward from that pattern to understand what produced it. Imagine looking through an old pane of glass that is warped over time. A candle on the other side might stretch into a smear. A straight line might bend. A small object might appear larger than it really is. At first, the image seems damaged. Then the distortion becomes useful. The bend tells you something about the glass itself. In gravitational lensing, the warped medium is not glass. It is space shaped by mass. The arcs and stretched forms are not errors in the instrument. They are evidence. They show that something massive lies in the foreground, even when not all of that mass shines. This is why lensing is so powerful. It can reveal hidden mass by showing how light behaves near it. It can also help telescopes study objects that would otherwise be too dim or too far away to measure clearly. In some cases, the universe places a natural magnifying lens in the line of sight. The telescope still matters. The mirror still gathers the arriving radiation. The detectors still measure it. But the cosmos itself has helped to focus the light before it ever reached the instrument. That changes the meaning of observation. Humanity is not only building tools and pointing them outward, it is also learning to use structures that already exist between here and the target. A massive cluster becomes part of the observing system. The foreground is no longer only an obstacle. It becomes a lens. It becomes a clue. It becomes a map of gravity. This is also where empty-looking space becomes less empty than it seems. The region between bright objects can still contain hot gas. It can still contain hidden mass. It can still shape the route of radiation crossing through it. The dark between visible systems is not simply a blank background. It participates. It bends, delays, magnifies, and distorts. To read deep space correctly, researchers have to study not only the object they want to see, but everything the light encountered along the way. A stretched arc in a telescope image may look like a smear at first glance. To a trained observer, it may be a message about two things at once. It says something about the distant source whose radiation has been bent. It also says something about the foreground mass that did the bending. One observation becomes layered. The far object, the intervening cluster, the hidden matter, and the curved path all belong to the same measurement. At cosmic scale, seeing is rarely simple. Light does not arrive untouched. It carries the history of the space it crossed. It carries the signature of gravity. It carries the evidence of structures that may not be directly visible at all. And this pushes the boundary of astronomy in a different way. The limit is not only how far the telescope can detect. The limit is how well researchers can reconstruct the route that the radiation took. Deep observation becomes an act of interpretation. It asks what the source was, what changed the light, what magnified it, what distorted it, and what hidden mass must have been present to make the image appear that way. The universe, at this scale, is not just the thing being observed. It becomes part of the instrument. And even the dark between the bright structures can behave like a lens, a map, and a record of what cannot be seen directly. A tiny patch of sky can look empty for one simple reason. No one has stared at it long enough. To the eye, it may be a blank part of the night. To a small telescope, it may show only a few scattered points. To a deep observatory, after enough collected light, that same patch can become crowded with galaxies. This is the strange power of a deep field observation. Instead of sweeping widely across the sky, the telescope holds its gaze on one narrow region. It gathers weak radiation patiently. It lets faint signals build until objects too dim for a shorter exposure begin to appear. The result can feel almost impossible at first. A piece of sky that seemed to contain almost nothing becomes filled with structure. Not just stars, not just nearby objects, entire galaxies. Many of the tiny marks in a deep field image are not individual suns at all. They are systems containing enormous numbers of suns, compressed by distance into small smudges, grains, and red points. A single speck may hold spiral arms that cannot be resolved clearly. Another may contain clouds of gas, older stellar populations, and regions where new stars are forming. From Earth, they collapse into dots because distance has taken away their visible scale. The mind wants brightness to mean importance. Deep astronomy teaches something colder and more difficult. The most meaningful object in the frame may be the one that barely appears. A faint red point may carry more information about the early universe than a large, bright galaxy in the foreground. This is because light is not only a signal from a place, it is also a signal from a time. The farther away a galaxy is, the longer its radiation has spent crossing space before reaching us. When researchers study the most distant galaxies, they are not seeing those systems as they are now. They are seeing them as they were when the light left them. That means a deep field image is not a single moment. It is a stack of different times placed inside one view. A nearby galaxy appears from a later cosmic era. A remote galaxy appears from a much earlier one. The image becomes a kind of time section through the universe, with distance turning into history. Redshift gives that history a measurable form. As space expands during the crossing, the radiation from remote galaxies is stretched toward longer wavelengths. Objects that released bluer or visible radiation long ago may arrive reddish or infrared by the time they are measured. That redness is not just a color choice in an image. It can be a clue that the signal has crossed an enormous span of expanding space. For the earliest candidates, the clue must be treated carefully. A red object is not automatically one of the first galaxies. Dust can redden light. A closer object can sometimes imitate a more distant one. Limited data can leave more than one possible explanation open. This is why the faintest discoveries often sound cautious when researchers describe them. Current measurements suggest the data is consistent with the object may belong to an early population. These phrases are not weakness. They are the discipline required when the evidence is barely above the threshold of detection. Imagine one tiny red dot in a deep image. It does not dominate the frame. It does not have the dramatic shape of a spiral galaxy or the glow of a bright nebula. It sits near the limit, almost swallowed by the surrounding dark. If enlarged too far, it may become only a softened blot of color. Yet inside that small mark is a claim about deep time. Its radiation may have left when the universe was far younger, before familiar structures had fully settled into place. It may come from a system where stars were gathering under conditions different from those around mature galaxies today. It may show a period when the cosmos was becoming transparent, structured, and increasingly filled with light. There is no grand appearance to match the scale of the idea. There is only a faint measurement and the work of proving what it means. This is why deep field astronomy can feel so humbling. It removes the expectation that discovery must look spectacular. Sometimes the universe announces a major clue as a nearly invisible mark. Sometimes the important thing is not the brightest object, but the one closest to disappearing into noise. And sometimes seeing farther means learning to respect how little information arrives from the farthest sources. There may be only a small number of photons. The shape may be uncertain. The color may depend on how different filters recorded the radiation. The distance may require comparison with models rather than direct simplicity. At this edge of observation, every conclusion has to be built from fragments. Astronomers compare wavelengths, brightness, surrounding objects, and possible sources of contamination. They ask whether the signal is real, whether it belongs to one object or several blended together, and whether its redness truly points to extreme distance. That work is slow because the stakes are high. A mistaken identification can turn an ordinary distant galaxy into a false record breaker. A careful identification can reveal something about the first generations of structure in the universe. The deep field, therefore, becomes both beautiful and severe. It gives the eye a crowded picture, but it gives science a harder task. The farther the observation reaches, the more interpretation matters. Light arrives weakened. Meaning does not arrive with it automatically. The meaning has to be earned. So the faint red dots remain powerful because they sit at the boundary between sight and inference. They are visible enough to tempt explanation. They are difficult enough to demand restraint. In them, astronomy becomes an exercise in patience, doubt, and scale. At the edge of sight, discovery does not always arrive as a grand image. Sometimes it arrives as a mark so small that it could almost be missed. And in that nearly invisible point, an entire early galaxy may be waiting to be understood. Far beyond Neptune, sunlight becomes thin. It still reaches outward, but its warmth is faint, its pressure weakened, and its presence almost symbolic compared with what it is near Earth. This is where the solar system begins to feel less like a familiar family of planets and more like a cold remainder. Beyond the last major planet lies the Kuiper Belt. It is not a hard border around the sun. It is not a wall. It is a broad outer region filled with icy bodies, frozen compounds, and ancient debris left from the early formation of the solar system. For a long time, Pluto seemed like a strange outlier. It appeared to be a lonely small world moving in the far dark, difficult to classify and separated from the clearer order of the major planets. But that picture changed. Pluto was not alone in the way people once imagined. It belonged to a larger population. The outer solar system was not empty after Neptune. It was sparse, cold, and difficult to see. but it held many objects that shared part of Pluto's story. That shift changed how Pluto itself was understood. It was no longer just the odd world at the margin. It became one member of a distant family of icy bodies. The Kuiper Belt is sometimes compared loosely to the asteroid belt, but the comparison only goes so far. The asteroid belt lies between Mars and Jupiter and is dominated by rocky and metallic remnants. The outer belt beyond, Neptune, is colder and richer in frozen volatile materials. Water ice, methane, nitrogen, and other compounds can remain locked there, in forms that would behave very differently closer to the Sun. The difference matters because temperature changes what matter can preserve. In the inner solar system, the sunlight alters surfaces, drives chemistry, and strips away fragile materials over time. In the far outer region, cold can keep evidence in place. An object there may preserve clues from the era when the planets were still forming, when small bodies were being scattered, gathered, disturbed, and left behind. The emptiness of this region has to be understood carefully. It can hold countless bodies and still be mostly empty. Two objects may share the same broad population, while remaining separated by distances so large that ordinary language becomes weak. From far away, the region sounds crowded. From within it, almost everything would feel isolated. Imagine drifting there in the dim reach of the sun. The light would not vanish, but it would lose the authority it has near Earth. It would fall softly across frozen surfaces, low and pale, barely enough to make the objects feel illuminated at all. A small icy body might turn slowly for ages, carrying craters, ridges, color changes, and frozen material across a surface almost untouched by warmth. There would be no bright planetary disk filling the sky, no thick atmosphere glowing blue around a nearby world, no busy field of objects passing close by, only distance, only cold, only a few points of light and the slow motion of preserved things. That is why the outer belt matters. It is not important because it looks full in the way a planet looks full. It is important because it stores what the active inner solar system has often erased. It is a frozen archive, not an archive with pages, labels, or explanations. An archive made of bodies that never became planets, surfaces that kept old scars, and material that remained far from the strongest heat of the young sun. Some short-period comets are connected to this outer population. They spend part of their lives in the colder regions, then move inward along paths that bring them closer to sunlight. As they approach the warmer inner solar system, frozen material begins to change. Gas escapes, dust lifts away, a faint tail can form. What looked inert in the dark becomes active under stronger light. A comet, then, is not simply a visitor from nowhere. In many cases, it is an outer remnant briefly made visible by heat. It carries material from far beyond the major planets into a region where human telescopes can watch it wake. The Kuiper Belt also points toward an even larger and less directly seen idea. Far beyond it, models of the solar system suggest the existence of the Oort cloud. That distant cloud has not been imaged as a neat structure surrounding the sun. It is theorized from comet behavior and from the way gravity may have scattered icy bodies into remote orbits over the solar system's history. This distinction matters. The outer belt beyond Neptune has known bodies we can observe more directly. The Oort cloud remains a much more distant and inferred reservoir. Together they show that the solar system does not end cleanly after the planets. It fades through populations, probabilities, scattered objects, and regions where the sun's control becomes harder to define. The first outer boundary we meet is therefore not a sharp line. It is a realm of leftovers. It is a place where failed planets, frozen fragments, and small preserved worlds continue circling in the far reach of sunlight. For the larger story of observation, this matters because the unknown is not only found in distant galaxies. Some of it begins inside our own system, past the planets we can name easily, in a cold region where the sun still rules, but no longer feels close. The darkness beyond Neptune is not empty. It is filled with old material, moving quietly, holding evidence from the time when our system was still assembling itself. And the first outer boundary we meet is not a wall at all. It is a frozen archive. There is a deep difference between seeing a dot and meeting a world. For decades, Pluto was mostly a remote point of light, measured from far away and surrounded by more assumption than detail. It belonged to the imagination partly because it was hard to see. It was distant, cold, small, and strange enough to carry the feeling of an outer limit. Then a machine crossed the darkness between the inner solar system and the far belt beyond Neptune. New Horizons did not make Pluto important. It made Pluto visible in a new way. The distant point became a place. Mountains appeared, plains appeared. Haze layered itself above the surface. Regions of different color and texture showed that this small world was not a dead ball of ice, resting unchanged in the dark. It was geologically complex. That alone changed the emotional weight of the encounter. A body many people had treated as a frozen leftover turned out to have structure, variety, and evidence of activity written across its face. The most recognizable feature was a bright heart-shaped region spread across part of the surface. Within it lies a broad plain of nitrogen ice. This plain is not just a visually striking mark. It points to movement, renewal, and surface behavior that made the world feel more active than many expected. The surprise was not that Pluto existed. The surprise was that it looked so alive in form. Not alive biologically, alive as geology, alive as a system still capable of reshaping itself. For a moment, the edge of the solar system stopped feeling like a storage shelf of frozen scraps. It felt like a place where small worlds could still have histories. But the deeper scientific turn came after the famous encounter. New Horizons continued outward. The mission moved farther into the Kuiper Belt, toward a much smaller target. This second object did not have Pluto's public recognition. It did not carry the same cultural weight. It was not a world people had argued about in classrooms or remembered from old planet charts. Its name was Arakoth, and in some ways, its quietness made it more revealing. Arakoth is a small Kuiper Belt object shaped like two joined lobes. The simple description is that two bodies came together and remained attached. The important part is how gently that seems to have happened. If the collision had been extremely violent, the structure would likely have been smashed, distorted, or broken apart beyond recognition. Instead, the two parts appear to have met slowly enough to preserve a joined form. That shape turned a small object into evidence. It gave researchers a clue about how some of the earliest planetary building blocks may have formed. Planetesimals are small bodies that helped build larger planets and other objects in the young solar system. They are not planets themselves. They are the pieces from which larger systems could begin. For a long time, one question was how such pieces first came together. Did they grow mainly through repeated impacts, with objects colliding again and again until larger bodies emerged? Or could some form more gently, as material gathered inside a local cloud and collapsed into small bodies moving together at low speeds? Arakoth strongly supports the second picture for at least some early objects. It suggests that small bodies in the outer solar system could form through slow local gathering rather than through constant high-speed violence from the beginning. That does not end every debate about planet formation. One object cannot explain every environment, every distance from the sun, or every stage of growth, but it gives a preserved example from a cold region where the past has not been erased as aggressively, and that makes it unusually valuable. Imagine this small reddish body turning in weak sunlight far beyond the major planets. No ocean moves across it. No forests grow. No weather system crosses its sky in the familiar sense. It does not announce itself with rings, storms, or brilliant clouds. It simply turns, slow and quiet, holding a shape that may have survived from the solar system's earliest construction. The two lobes sit together like evidence left in plain sight. Not dramatic evidence, patient evidence. A form that says the first steps of building worlds may have been softer, slower, and more organized than a picture of constant collisions would suggest. That is what makes the encounter so strange. The famous world gave the mission its spectacle. The smaller one gave it a more delicate clue. Pluto showed that the outer belt could contain complexity. Arakoth showed that the outer belt could preserve memory. Together, they changed how the region beyond Neptune felt. It was no longer only a distant zone of leftovers. It became a place where old processes could still be studied, through bodies that had kept their original character. The spacecraft itself made this possible by crossing from remote astronomy into direct exploration. A telescope can measure brightness, color, motion, and sometimes shape. A flyby can reveal surface form, geology, texture, and context in a way that turns a target from an idea into a physical place. That difference matters because planetary science often depends on details too small for distant viewing. The curve of a surface, the smoothness of a plane, the way two lobes meet, the absence of violent scars where violent scars might have been expected. Each detail changes the story that can be told. And at the edge of the solar system, where objects are small and sunlight is weak, even a brief close look can become decisive. New Horizons did not stay. It could not orbit these worlds. It passed by, gathered what it could, and continued into the dark beyond them. That makes the evidence feel even more fragile. A small machine, moving at tremendous speed, crossed the right path at the right time and turned distant objects into known places. Afterward, the worlds remained where they were, cold, remote, quiet. But they were no longer only points in a catalog. They had surfaces, shapes, and histories. This is why the smaller body matters so much. The largest or most famous object is not always the one that carries the clearest answer. Sometimes the clearer clue is preserved in a small form that avoided the violence, heat, and disruption that changed larger worlds. Sometimes the object at the edge tells us about the beginning, and sometimes the smallest world explains the larger story more clearly than the famous one. Two old machines are still moving outward through the dark. They were built by human hands, launched from one world, and sent toward planets that once existed only as distant points of light. The world that created them has changed many times over. Computers have shrunk. Cameras have transformed. Entire generations have grown up under a sky where these spacecraft were already far beyond home. Yet Voyager 1 and Voyager 2 continue on their outward paths. They are no longer young missions. They are aging systems, powered by fading energy, speaking across distances that turn every signal into a test of patience. Their story began as a planetary mission, not as an attempt to become eternal messengers. The goal was practical and extraordinary at the same time. A rare arrangement of the outer planets made it possible for spacecraft to visit several giant worlds, along one carefully planned route. The probes could not simply carry enough fuel to force their way across the outer solar system. Instead, they used gravity. Each planet became a turning point in the route. As a spacecraft approached a giant world, the planet's gravity bent its path and changed its speed. The maneuver had to be timed with extreme care. Too early, and the route would fail. Too late, and the chance would be lost. Handled correctly, the planet acted like a slingshot, giving the machine the energy needed to continue farther outward. This made the outer solar system into a sequence of opportunities. Jupiter was not only a destination, it became a way forward. Saturn was not only an object to photograph, it became another part of the path. The same logic carried Voyager 2 onward to Uranus and Neptune, extending the mission far beyond a single encounter. The discoveries changed the way those worlds were understood. Jupiter became more than bands and storms. Its moon, Io, revealed active volcanoes, turning a small world into one of the most geologically active places known. Saturn's rings, already famous from Earth, became far more complex when seen up close. They were not smooth ornaments around a planet. They were structured, divided, braided, and shaped by gravity in subtle ways. Uranus appeared with a strange magnetic field, tilted in a way that did not fit the simple expectations people might carry from Earth. Neptune, far from the Sun, showed powerful weather and a dynamic atmosphere where many expected a colder stillness. The moons also mattered. They were not just small companions circling larger planets. They became worlds with surfaces, histories, fractures, atmospheres, volcanoes, ice, and possible hidden processes. The mission compressed an entire outer solar system education into a few passing encounters. It did not answer everything. It made the questions sharper. Before the Voyagers, many outer worlds were known mostly through blurred observations, calculations, and patient ground-based study. Afterward, they had faces. They had storms. They had rings with structure and moons with character. The distant planets stopped being only names at the edge of diagrams. They became places with their own evidence. But the planetary encounters were only the first life of the mission. After the cameras had done their most famous work, the spacecraft kept moving. Their paths carried them beyond the planets, beyond the region where the sun appears large and commanding, into a colder environment where the mission became quieter and more difficult. At that stage, the dramatic images were no longer the center of the story. The important measurements came from instruments studying particles, fields, and the changing environment around the probes. They were no longer only looking at worlds. They were feeling for a boundary. From Earth, communication with them became an act of listening across an almost impossible distance. A command sent outward takes time to arrive. A reply takes time to return. There is no instant conversation with a machine that far away. The signal travels at the speed of light, yet the distance is so large that even light must be waited for. Imagine a radio message crossing the black between the planets and Earth. It spreads outward, weakens, and arrives with less power than the faintest everyday electrical glow. It reaches great antennas on the ground as a nearly vanishing trace. Inside that trace may be a reading from beyond the familiar planetary region, a change in particles, a shift in cosmic rays, a measurement from an environment no human being has ever entered. The message is small, but the distance behind it is enormous. There is something deeply human about that exchange. A machine built in the early space age keeps speaking in a technical language of numbers, voltages, and instrument readings. On Earth, people keep listening. They decode the signal, correct for delay, manage declining power, and decide which instruments still matter most as the available energy slowly falls. The spacecraft are not immortal. Their power sources weaken. Their instruments cannot all keep working forever. Their voices will eventually fade beyond usefulness. That future gives the mission its quiet emotional weight. The machines are not alive, but they carry human intention farther than any human body has traveled. They carry records, engineering decisions, scientific questions, and the long patience of people who chose to keep listening after the first spectacular discoveries were over. Voyager 1 and Voyager 2 are now beyond the sun's dominant bubble of solar wind influence. That statement can sound simple, but it changes the scale of the story. The solar system is often imagined as a collection of planets ending somewhere after Neptune. The Voyager showed that another kind of boundary exists far beyond the planets. It is not a border drawn around the last orbit. It is the outer reach of the sun's wind and magnetic influence. By moving through that region, the probes helped reveal that our star does not merely shine on the solar system. It fills it. It presses outward. It creates a surrounding domain that must eventually meet the material between stars. This is where the planetary mission became a boundary mission. The same spacecraft that showed us volcanoes, rings, tilted magnetism, and distant storms later measured the weakening influence of the sun itself. The arc of the mission feels almost impossible in its simplicity. First, they showed us the worlds. Then, they showed us the space beyond the worlds. And finally, they showed us that even the sun has a reach that can be crossed. The Voyagers did not only reveal planets. They revealed that our star has an edge of influence. The sun is not only the light at the center of the solar system, it is also a source of motion. From its outer atmosphere, it releases a constant stream of charged particles into surrounding space. This stream is called the solar wind. It flows past Mercury, Earth, Mars, Jupiter, and the worlds beyond them. It does not stop at the last planet. It keeps moving outward, carrying our star's influence into a region far larger than the planetary orbits alone suggest. The solar wind is invisible to human eyes. It does not look like wind on Earth. There are no leaves to shake, no clouds of dust blowing across a road, no sound moving through air. It is a flow of particles and magnetic fields, spreading outward from the sun through space that otherwise seems almost empty. Because of that flow, the solar system is surrounded by a huge bubble of influence. That bubble is called the heliosphere. The name is technical, but the idea is simple enough. The sun pushes outward. The material between stars presses back. Somewhere far beyond the planets, those pressures meet. The heliosphere is the region where the sun's outward flow still shapes the environment more strongly than the surrounding interstellar medium does. The interstellar medium is the thin mixture of particles, fields, and radiation that exists between stars. It is not empty nothingness. It is sparse, but it still matters. It has pressure. It has particles. It has magnetic structure. And when the sun's outflow reaches it, the meeting is not clean. The first important boundary is called the termination shock. Here, the solar wind begins to slow sharply. For a long time, it has been moving outward faster than the waves that can travel through it. Then it meets growing resistance from the surrounding environment. The flow changes. It loses speed. It becomes more disturbed. The termination shock is not a solid surface. A spacecraft does not hit it like a wall. It is a change in conditions, measured through particles, fields, and speed. Beyond that region lies the heliosphere. This is a disturbed outer layer where the solar wind has slowed but has not fully surrendered to the interstellar medium. The heliosheath is not a calm shell. It is uneven, pressured, and shaped by forces coming from different directions. Particles move differently there. Cosmic rays become more important. Magnetic fields complicate the picture. Older, simple drawings often made the outer solar boundary look smooth, as if the sun sat inside a neat rounded envelope. The measurements did not support something so tidy. The outer region is more complex than a clean diagram can show. Farther still is the heliopause. The heliopause marks the point where the solar wind no longer dominates the surrounding environment. It is the boundary between the sun's domain and interstellar space, in the practical scientific sense. But even this boundary is not a painted line across the dark. It shifts. It responds to changes in solar activity. It is shaped by the direction of the sun's motion through the galaxy and by the pressure of what lies outside it. The word boundary can make the mind imagine a gate. This is not that kind of threshold. It is more like pressure meeting pressure in the open dark. Now imagine a spacecraft crossing it. There is no flash. No sudden glow appears in front of the camera. No visible wall marks the passage. The machine moves through space as it always has, cold, silent, and far from any human hand. Only its instruments know that something has changed. The number of particles from the sun falls. The number of high-energy particles from beyond the heliosphere rises. The magnetic environment behaves in ways that must be read carefully. A crossing like that is almost the opposite of a dramatic border. It is a quiet change in measurements. The spacecraft enters a different environment, not because space looks different, but because the balance of influence has changed around it. That is what makes the Voyager measurements so important. They did not show a glowing rim around the solar system. They showed that the outer reach of the sun can be detected as a physical transition. The boundary had to be read through data. It had to be inferred from changing particle counts, cosmic rays, plasma conditions, and magnetic behavior. That makes it less visually simple, but more scientifically powerful. It reveals that the solar system is not just a list of planets around a star. It is an environment inside a larger galactic environment. Our star carves out a region around itself, and that region moves through the material between stars. The shape is not fixed like a glass sphere. It is formed by motion, pressure, and changing conditions. At times, the sun's activity grows stronger. At other times, it weakens. The surrounding interstellar medium is not perfectly uniform either. The result is a boundary that breathes in a physical sense, expanding, compressing, and changing its structure over time. This is difficult to picture because the scale is so far beyond ordinary experience. On Earth, boundaries often have visible signs: a coastline, a fence, a doorway, a shadow on the ground, at the edge of the sun's influence. There is nothing like that. There is only a region where one environment slowly gives way to another. The idea changes how the solar system feels. It is not a small collection of objects floating naked in open space. It is wrapped in an invisible domain made by the star that holds it together. That domain shields, filters, and shapes some of what reaches the planets from the wider galaxy. It does not make Earth safe from everything. It does not seal the planets away, but it means the sun has a presence far beyond its light. Long after sunlight has become weak, the wind and fields of our star still define a surrounding zone. And beyond that zone, the galaxy begins to press in more directly. The edge of the solar system is therefore not a clean line drawn in space. It is a changing region of pressure, particles, and fields. An edge means something different if space itself has a shape. In ordinary life, an edge is easy to picture. A table ends where the wood stops. A room ends where the wall begins. A road ends where the pavement breaks or turns into something else. But the universe does not have to behave like an object placed inside a larger room. Space is not simply a container holding galaxies. It is part of the thing being studied. Its geometry decides how distance works, how light travels, how paths separate, and what the word forever might actually mean. This is where the question becomes stranger than a physical border. The universe may have no wall at all. Its shape alone may decide what can ever be reached. The simplest model to picture is a flat universe. In this case, parallel paths remain parallel as they continue. A triangle drawn on a flat surface behaves the way school geometry says it should. Distances grow in a way that feels close to common sense, at least compared with the other possibilities. If space is flat on the largest scales, it can extend onward without curving back on itself. That does not automatically prove it is infinite. It means only that, in the part we can measure, space behaves as if it has no large overall curvature. This distinction matters. A flat, observable region does not reveal the whole universe. It tells us what geometry looks like inside the area from which information has reached us. Beyond that horizon, the full structure may still be larger than anything our measurements can settle. A positively curved universe feels less intuitive. The closest comparison is the surface of a sphere. A traveler moving across that surface can go forward without ever finding a sharp edge. There is no cliff at the end of the surface. No wall appears. No sign announces that space has run out. And yet, the path can eventually bend around in a way that returns the traveler toward where they began. The surface is finite, but it has no boundary in the ordinary sense. This is difficult because the comparison uses a surface we can see from outside. The universe gives us no outside viewing position. We cannot step away from reality and look at its shape from beyond it. We are inside the system whose geometry we are trying to measure. That makes the question both scientific and deeply disorienting. A finite universe does not necessarily require an edge, and an endless feeling path does not necessarily prove an endless total space. A negatively curved universe offers a different picture. In that model, paths that begin parallel can spread apart. Space opens outward in a way that makes separation grow more aggressively than ordinary flat intuition expects. The usual comparison is a saddle-like surface, though even that is only a shadow of the real idea. The important point is not the picture itself. The important point is what the geometry does. It changes how routes behave. It changes how volumes grow. It changes how far apart distant regions become, as light and matter follow the structure of space. These possibilities are not just clever drawings. They change the meaning of the cosmic horizon. If space curves back on itself, then the universe may be finite without having a border. If it is flat and endless, then the observable region may be only one limited portion of something without a final outer rim. If it is negatively curved, then distance may open in a way that makes the unreachable feel even more deeply unreachable. Each model changes what people mean when they ask what lies beyond what we can see. That question may not have the shape of a map. It may have the shape of geometry. Picture traveling forward through space with no marker ahead. The galaxies thin and change. Light from familiar regions falls behind. The path continues. There is no wall, no final curtain, no last stone at the border of reality. Only more distance, more expansion, and a growing uncertainty about what forward means on the largest scale. In one geometry, forward may mean entering new regions without end. In another, forward may eventually curve through a structure too large to recognize from within. In another, forward may carry paths apart so strongly that return becomes meaningless. The traveler would not feel the shape directly. There would be no sudden turn in the floor space. The shape would be revealed only by measurements, by light, by angles, by the way distant patterns appear across the sky. Current observations suggest that the observable universe is very close to flat on large scales. That is a powerful result, but it has a limit built into it. We can only test the part of the universe whose information has had time to reach us. If the whole structure is much larger than the observable region, then even a slight curvature might be too small for us to detect from our position. It would be like standing on a tiny patch of an enormous surface and trying to decide whether the full surface bends. The ground beneath you may look flat. The total form may still be beyond your local view. This is the quiet difficulty behind cosmic geometry. The measurements are real. The limits are real too. Near flatness inside the observable region does not give humanity a final picture of everything beyond it. It gives a careful statement about what can be measured from here. That carefulness is not failure. It is the price of living inside the universe, rather than outside it. The question of an edge, therefore, changes. It no longer asks only whether there is a boundary somewhere in the dark. It asks whether the idea of a boundary belongs to the wrong mental picture. Perhaps space does not end like a road. Perhaps it continues in a form where ending and returning are not opposites in the way human intuition expects. Perhaps the part we can see is only a local portion of a structure whose full geometry never fits inside observation. The universe may not need a wall to keep some regions beyond reach. Its shape alone may be enough. Across the whole sky, there is a signal older than stars as we know them. It is not starlight. It is not the glow of a galaxy. It is not a beam from one object traveling cleanly through space. It is a faint remaining radiation from the early universe, stretched and cooled until it now fills the background of the cosmos. This is the cosmic microwave background. It is sometimes described as ancient radiation left from the early universe, but that simple phrase carries enormous weight. It gives researchers a way to study conditions from a time before galaxies had become the familiar structures seen today. It is not a photograph of the beginning itself. It is a map of a later moment when the universe had cooled enough for radiation to travel more freely through space. That radiation still surrounds us. It arrives from every direction, and inside its nearly even glow are tiny differences that matter deeply. Those differences are small, but they are not meaningless. They help researchers test models of the universe's age, contents, expansion, and early structure. They are like slight variations pressed into an old surface, faint enough to require careful measurement, but important enough to shape modern cosmology. The cosmic microwave background is therefore not only a relic, it is a measuring field. It lets scientists compare theory with the actual pattern of the early cosmos. For that reason, any unusual pattern connected to it immediately attracts attention. One of the most controversial ideas tied to large-scale structure is known as dark flow. The claim was associated with a research team led by Alexander Kashlinsky. The team reported evidence that many galaxy clusters appeared to share motion toward one region of the sky. That statement has to be handled with care. It was not a simple image of clusters visibly racing across space. It was an inference drawn from subtle measurements connected to the cosmic microwave background and the behavior of galaxy clusters. The reported motion seemed to point in a preferred direction. If such a flow existed on a very large scale, it would be difficult to ignore. The universe, on its largest observable scales, is usually expected to look broadly uniform when viewed from far enough away. There can be clusters, filaments, voids, and immense structure, but no special direction should dominate everything. A shared motion of many clusters toward one region would therefore raise a difficult question. What could create such a pattern? One provocative interpretation was that the flow might preserve a trace of something beyond the observable horizon. Another possibility discussed around the idea involved conditions connected to cosmic inflation, the early expansion that may have separated regions of space so completely that they can no longer exchange information with us. This is where the idea becomes dangerous if it is spoken too strongly. A disputed signal is not proof of another universe. It is not proof that something outside everything we see is pulling on galaxy clusters. It is not permission to turn uncertainty into a claim. At most, if the reported pattern were real, it could suggest that the standard picture was missing something about very large-scale motion, or the early conditions of the universe. That is already extraordinary enough. It does not need exaggeration. The skeptical side matters just as much as the claim. Later analyses did not confirm the signal in the same way. Work using data from the Planck Space Observatory, among other efforts, failed to establish dark flow as a settled feature of the universe. That does not make the original question worthless. It places it where it belongs, inside an unresolved and disputed part of cosmology. Science is not only a list of accepted discoveries, it is also a record of strange signals that were tested, challenged, weakened, or left uncertain after better measurements arrived. This is especially true at the edge of observation. When the signal is subtle, the method becomes part of the story. Researchers must ask whether the effect is real, whether it comes from the clusters themselves, whether it comes from how the data was processed, or whether noise and assumptions have shaped the result. They must separate motion from measurement. They must separate a pattern from a preferred interpretation. And they must separate an exciting possibility from evidence strong enough to carry it. Picture a map of the oldest radiation spread across the sky. It does not look dramatic in the ordinary sense. It is covered in slight variations, tiny changes in temperature and pattern, so delicate that they would mean almost nothing without instruments and mathematics. To one method of reading, a faint feature may look like a clue. To another, it may fade into statistical uncertainty. The map is not lying. The difficulty is knowing how much can honestly be asked of it. A mark in old radiation can be a physical trace. It can also be a limit of interpretation. That tension is what makes dark flow interesting without making it confirmed. It sits near the boundary between data and desire. Human beings want the edge of the observable universe to leave a mark. They want the darkness beyond the horizon to have some fingerprint inside the part we can measure. But wanting a trace is not the same as finding one. The most careful version of the dark flow question is not a declaration. It is a warning about scale. The observable universe may not reveal the full universe. Our measurements may contain hints, gaps, and anomalies that tempt larger explanations. Some of those hints may survive. Others may disappear under sharper analysis. The only honest way forward is to let each possibility remain exactly as strong as the evidence allows. That restraint is not dull. It is what keeps wonder from becoming fiction. There may be strange patterns in the oldest radiation. There may be limits in the models used to read them. There may be questions that stay open because the horizon itself prevents a final test. But a strange possibility is still not the same thing as proof. And science is at its most honest when it can let the unknown remain unknown without pretending it has already been solved. Every boundary in space becomes stranger the closer it is examined. At first, a limit sounds like a place. It sounds like somewhere a traveler could arrive, pause, and point outward from the final known side. But the universe rarely gives us that kind of simplicity. The edge of sight is not the same as the edge of matter. The edge of the solar wind is not the same as the edge of the solar system in every possible sense. The edge of telescope sensitivity is not the same as the edge of reality, and the edge of the observable universe is not a wall around existence. It is a limit created by light, time, expansion, and position. We are not outside the cosmos looking in. We are inside it, receiving whatever information has had time to reach us. That one fact changes everything about the question. The observable universe is the part from which light and other signals can arrive here. Beyond that region may be more space, more matter, more structure, and more history. But if its light has not reached us, or can never reach us, then it remains outside observation in the most physical sense, not hidden behind a door, not concealed by choice, simply separated by the behavior of space and time. Cosmic expansion makes this even harder to accept. Some regions are not merely far away, they are becoming more unreachable as space expands between them and us. A signal from such a region may never cross the growing distance. Even if it began moving toward us, the space it must cross can stretch faster than the signal can overcome. This does not mean the signal moves faster than light. It means space itself changes the meaning of separation. The result is a universe where some places may remain forever outside causal contact. They may exist. They may have galaxies, stars, planets, and their own histories, but no message from them may ever become part of our sky. That is not a technical detail. It is a deep limit on knowledge. It means that better instruments can expand the circle of what we measure, but they cannot automatically remove every horizon. A larger mirror can gather weaker radiation. A colder detector can measure fainter infrared signals. A probe can cross from one physical environment into another. A better map can sharpen the oldest radiation we can see. Each achievement matters. Each one moves the line outward, but none of them turns humanity into an observer of the whole universe from above. We remain local. We remain embedded. We remain dependent on signals that the cosmos permits to reach us. This is not defeat. It is the condition under which astronomy exists. To study the universe is to work from inside a moving boundary. Knowledge grows, but it does not become unlimited. The dark beyond the measured region is not empty just because it is silent. It is silent to us. That difference matters. A thing can be unreachable without being unreal. A region can be beyond sight without being beyond existence. A question can be meaningful even when no final instrument can settle it. There is humility in that, but also a kind of strength. Human beings have never needed certainty about everything in order to keep looking. They looked upward before they understood what stars were. They built lenses before they knew how large the galaxies would become. They launched machines outward before they knew where the sun's influence truly faded. They mapped the oldest radiation before they knew which strange patterns would survive closer inspection. Again and again, The boundary moved, not because the unknown vanished, because the light grew wider. Return to the image of a fire in the dark. At first, the flame shows only the ground nearby. Stones appear, branches appear, the hands around the fire become visible. Then the flame grows, and the circle widens. More of the surrounding world enters view. The shapes at the edge become clearer. The ground that once seemed empty turns out to hold marks, paths, and objects waiting just outside the earlier glow. But beyond the firelight, the dark remains. It has not been defeated. It has only been pushed farther away. That is what human observation does. It enlarges the circle. It gives form to what once looked like absence. It turns faint radiation into history, invisible particles into boundaries, and tiny marks into galaxies. But it also teaches that every new circle has an outside. The unanswered is not the enemy of knowledge. It is the space knowledge grows into. And perhaps that is why the darkness above us still matters. Not because it promises a final border, not because it hides one last simple answer, but because it reminds us that seeing farther is not the same as reaching the end. The universe may not have an edge waiting for us like a line on a map. It may only have horizons that move, limits that change, and regions whose light will never arrive. So humanity keeps looking outward from its small circle of fire, not because the dark will end, but because pushing against it is part of what we are.